So yeah, well, any questions? Otherwise, we're just gonna continue with the live coding. So I think, yeah, I think I was writing the permutations, but just giving a few changes that you may want to avoid repeating certain permutations. So you can think about the way that you write it. Okay? And the pop operation is one that's perfect for this kind of um, coding because you are taking one element out of your list, and then for the rest you are doing the recursion and doing all permutations. So right. I need to return. Oh yeah, so is that question about permutations? I've just fixed the code and also added a few comments. So that should work. And yeah, so basically the idea here is that since you want to identify whether there are neighbors that are the same, right? So if you have something like 3, 2, 2, 3, then 3 and 3 at the beginning and the end, essentially they're gonna do the same thing. So here, the usual way is to firstly sort it. And then if there are identical elements, then you can easily just compare with the one before or the one after. And then everything is pretty standard. As long as you are basically for the starting point for the index 0, you certainly wanted to start with the permutation. But then for the latter elements, you only want to do them when they are not the same as the prior. So let's say if you have 1, 1, 2, 2, right? If you have 1, 1, 2, 2, then okay, for the first one, I'm gonna take it out and then put it at every place. You do the permutation of 1, 2, 2 and then add one at the front. And then for the next one, then you remove it, it's gonna still be 1, 2, 2. So you don't really want to do that. And then you're gonna continue with 2, which is different. So you take that 2 out and then you permute 1, 2, 2, 1, 1, 2, 2. Oh, excuse me, 1, 1, 2, and then you put 2 at the beginning. And then the last two, you're not gonna get anything new. So still you're gonna avoid that element. So essentially it's gonna be 2 times of this if condition. Okay. And then of course when you are doing the pop, essentially you are manipulating the list. So you do want to get a copy. Okay, so if you're doing a pop to a list, that list will be modified. It's really unlike the strings. Okay, so for strings, that will not be an issue. Every time you do a operation to a string, it will just return you a new string. But here, it's gonna operate on your original list. So when you pop the index I, then that temporary copy is gonna change. So that's where you permute all the that temporary copy, which is by removing the ith index. Okay, and then you put that element up front. Just a list plus that remainder list is gonna be just combining it together. So and now you have this kind of 1, 1, 1, 2, 2. That's saying what? That's saying actually you have 4 elements, and then you are just considering where you want to put those ones. So it's going to be a 4 choose 2, which is like a 4 times 3 over 2 times 1, which is a total of 6. Okay, so indeed you are not really repeating too much for your permutations. So let's say what happens if you have something like 2, 1, 2, 1. Okay, so it's essentially gonna give you the same result. Uh, and this is in a sense, it's not super. Let me see, 1, 1, 2, 2, 1, 2, 1, 2, 1, 2, 2, 1. So it's sort of alphabetic in a sense. Okay, lexicographic ordering. So that's nice. And then if I change the input, I should expect the same output because at first, once I sort it, it's going to be the exact same list. Right? Okay, so yeah, this is the way that I would approach it to avoid making 4 factorial every time. Make sense? And then of course, the averaging of the list is nothing super uh, special. So use the function from exercise 4 challenge. Can you compose these functions to compute the averages of this under all its so yeah. So basically, the averaging is nothing super new. but you also realize to check your answer, right? So it's basically you permute all the elements in any always possible. So essentially, the average is gonna give you the same value across the vector. So it's gonna be the sum of your original list dividing by the number of elements, right? So that's the average. So you can always compute and check with your theoretical observation there. Yeah, so make sure to have your permutation um, implementation correct. Okay, so that um, still somehow, yeah, this accesses your well, let me correct it. It assesses your um, implementation on recursions, uh, especially. So for permutations, if you want to write it on your own, indeed, utilizing recursion is a very helpful way. Right. So let me see if there's anything. Okay. Yeah, make sure to think about number two. So number two is you make a dictionary and you just realize, let's say you have 12 elements, is going to be key one, key two, all the way up to key one, two. And then you're associating to one, right, for the last key. So All right, so now for exercise two, basically, since the dictionary is not really ordered, but it has keys and the values, so everything is sort of labeled with string indices. Okay, so what you can do here is indeed for every uh, for every p, okay, you define your associate and output. So just like what we design. Okay, so it's gonna be key one relating to n. So that's your index zero is gonna add one to get you the number there, and then for the output it's gonna be n minus one, n minus I, right? So that's mm, relatively straightforward, but you are not able to directly add just like what you have for or append for this. So let's try also append, uh, which should not be able to do. But you see, using the curly brackets for a key associated to the output is a reasonable operation. Well, in terms of the dictionary, but still, you should think about the way that you can do it. Okay, but it's not in the traditional list way that you can append or add, which is unfortunate. Yeah, so there isn't such an attribute. Okay, append for dictionary. Mm. Right. So yeah. So just make sure. So basically, I think the trick here is mainly you need to uh, sort of customize your the way that you do your key. Okay, so essentially, in real data, you may have a number of elements with specific strings, right? But then when you are writing something on your own, just coming up with a systematic way of building your dictionary, you may think about something like this. Okay, so in the real world, maybe you don't have a a lot of options for that, but on your own um, dictionary, you can do something. Just also make a sort of like a correspondence mapping for you to remind yourself what they mean. That's relatively efficient. Right. Um, Well, exercise three, I would say it's like a kind of like conceptual question. So in fact, there are many ways to generalize distances, right? So let's say you have to have the inputs of same length for Hamming distance. So if not, then just like an idea that's mentioned earlier, so you substitute certain number of characters to make them equal length, or um, so yeah, there's always something that you can do to it. So there is not a unique answer, but you can also combine different ways to compute the distance altogether, because one metric plus another metric still gives you a different metric. Okay, so indeed there are many options. Number four, write a function that takes in a list of lists equal length and produces a level. Okay, that's the homework question. Yeah, so exercise 4, I would say, yeah, it's just like what you write in homework. Basically, keep an average list, which should be the same length of your individual list. Okay, so we assume all the lists have the same length, so you can pick okay the index zero, the zeros list, okay, to be the one you refer to, and then of course every time you are summing up the elements at all the ith location. Okay, so it's gonna be list J, and then you look at the ith location overall, and then sum, and then do the average. And of course, once you get that temporary value, and then just append. So there's nothing really special here. And of course, whenever you do it, just make sure to check your final answer. The list that we started with is like 1 2 1 2, right? So you're gonna expect an average of 1.5 throughout. That's number 4. Number 5, yeah, number 5 is the commutation. Yeah. Any questions? So yeah, well, this one, I think this one is sort of getting f more familiarized with certain data types, data structures, so for example, dictionary. And then the permutation is something like revisited a little bit. So mm, then let's if all good, then we can jump into section 7. Or if you guys need a little bit time to continue, that's totally okay. Just let me know. Yes?
For lectures 4 and 5, to post your post.
Let me, yeah, let me do that. Let me think. I'm displaying this page. So yeah, what I want to do is do it now. This other. Wow, that's so loud. Let me try this. Okay, that's better. Uh, Here. 3. What? I don't know why it's still moving. So 3, 4. Okay, 4 and 5, right? I do know where it is, but okay. So for certain newer versions of OneNote, the file printout is actually pretty neat. But you definitely want to make sure that your Windows version and the OneNote version is sufficiently new. Wait, why? Okay, that's that. Uh, we are 4, right? So yeah, that's make sure that's for your own studying purposes because there are certain things actually, it's sort of like experiments, but indeed, this I think the material are sort of standardized for this course. So other section may still use similar questions for practice purposes. 5 is here. right? And of course, if you want to make, let's say, copies of the notes, I think you will be able to do so. Just make sure if you want to keep the copy, just do it at the end of the semester or near the end of the semester. Basically, it's export. You can do a section and then like PDF, right? So that's actually pretty convenient. Okay. So that's also the way that I write my own preparation of notes and then print out and then bring to class. Yeah, this is a really nice tool. Okay. So yeah, so make sure it loads on your end because yeah, it takes a few seconds to synchronize. All right. So that's good. Okay. Section 7. Okay. So yeah, we're getting into that sort of like the end game of the coding part, I would say. Of course, there's a lot to enhance and develop further for the computational or for the coding skills. But then we still also would like to discuss certain things about like plotting and certain basics of machine learning, like data models. But then for the objective-oriented programming, it's gonna start from lecture 7. So, but at least today we can wait. Yeah, we can talk about yeah, well, list comprehension. So this is a really important topic which sort of combines certain tricks that we have seen from before. Let me also share my screen from the laptop. So we're 6, wait, 7. Let me stop the sharing here. Wait. Oh, did I get into the wrong meeting? I think I probably have. Oh, I see. Okay. Okay. Just one more confirmation I have to do on my side. I see. All right. So, list comprehension. This is actually a really nice way that you can condense your code. Okay. So, firstly, about the strings. So, indeed, we have for the colon notation right here. So, there are quite a few things that we can do as sort of like default inputs. Okay. So, here, notice if X is a list, string, and tuple or iterable, basically for these kind of objects that you have indices, natural number indices, then you will be able to do things um, beyond the simple slicing. Okay. So remember slicing, when we are doing slicing, this is I colon J. This is starting from I and ending at J minus 1, right? So that's what we have seen from before. But actually, there's a third, I would say, third argument, okay, for this operation. That S is actually the increment, okay, so it's like the step size, okay. So if you sort of remember, this is like the start, and then start plus step, and it just all the way goes up to the point where the thing start plus k times, let me use a cross, k cross step. As long as this is less than j, less than stop, then we are fine. Okay, so this is the new data structure, okay, that they construct. But this s value could be -1, -2. which is very interesting. So this is a list in reverse, okay, taking every second entry. So indeed, if you want to do a one-liner of, let's say, reversing a string, actually you can do so. So that's going to be X, and you set the things before the first and second colon as default, which is essentially 0 all the way to the length of your string, and then finally -1. That's reversing the entire string. Okay. So earlier we were doing that kind of either a recursion or a loop implementation of reversing a string, right? But here you can utilize this kind of operation in shorthand. Of course, this way is essentially built in, so it's going to be more efficient. Okay, computationally speaking. This is the built-in inverse, reverse. And of course, this colon without any inputs right here, this is the shallow copy that we mentioned earlier. So sometimes for a data structure, let's say a list, right? So if you want to make a copy before manipulating the data, so that's something you do. Okay, so this is shallow copy. Yeah, right. So that's certain list operations. So yeah, let me see. So basically, the code cell here is something you can definitely run and see if the our outputs make sense. So basically, you have a long sentence of as a string X. So basically, print 0:29. This is basically printing the first 29 characters within your string, and then printing that ::2 is actually saying I print the indices 0 to basically the odd indices. Excuse me, the even indices. And then with the -1, that's the step is going to be just reversing the whole string. And indeed, for that banana, which is relatively short to see clearly, you have so just indeed reversing the whole string. And so for strings, that's really handy that you will directly get a reverse string as an output. So that tells you what? It tells you indeed certain operations you of course you can implement yourself to get a deeper understanding, but of course there will be other ways that can be computationally more efficient. Okay. So that's also something you can do in list comprehension. What we mean here is that if you want to construct a list, so you may not really have to write a loop every time. So earlier, just now when we were doing that averaging of the number of lists, right? So it's a loop. It's like a double loop. So for certain lists, okay, you are trying to manipulate and you know the expression really clearly, then you don't really have to write the loops that much. Okay, so it can be done in one line. So the idea here is you need to specify the expression, and then basically this is sort of the mathematical way that you are writing some loop, but then you are putting it down in syntax. Okay, so basically it's for all the items in the list. Okay, so basically the circled expressions are what you can change freely as you will, and what in addition is that it can be multiple folds. Okay, so let's say you have one list and so you have two lists, okay? You want to do something to the elements to both of the lists and then putting them together. Then it can be for item one in list one, for item two in list two. So it's sort of like a free. Okay? But of course, make sure that the expression that you have is reasonable for the elements that you want to construct. Okay, so these are elements of your new list. Okay, so that's that part. So as an example here, let's say you have the string human. So if you want to put every character within as a separate element in your list, right? So it's human. You can do a loop. So here, um, this is saying, okay, every time I pick up, so this is for I in H. Okay, so sometimes you can say, okay, I want to get the indices, and then I run through the indices to get the elements. Here, this is the alternative way that you don't really specify the indices. You just say for element I in my list H, okay, for um, I representing any element. H is your string as a list of your characters. But basically, you're saying, okay, for every element here, I'm just appending to the letters that I'm constructing. So that's this for loop that you can write. But of course, you don't really have to do that. You can just do because for and the list they are here, and essentially you are not really doing anything special to your list. So essentially, you just put an I there for to indicate that okay, I'm putting that I as one of the element. Okay, so in my new list. So that's one line. So when they talk about the one-liner Python code, that's actually this. Okay, list comprehension. And of course, here the example above is saying, okay, of course, for that expression part, okay, I can do things as I want. So if I have two times I, let's say what, let's say I'm having two copies of that character there, so it's gonna just be repeated. It's gonna be HHUUMMANN, right? So that's the idea of list comprehension. So as long as your expression and the way that you choose the element from your particular list, they're all reasonable, then this is indeed sufficient. So as a so yeah, so on your end, make sure to play with the cells. But that's just really uh like simple to run. Oh, by the way, here there's a question, right? So why do we use print here and not return? So what do you think? Exactly. When there's a return, you sort of need a function. We don't really have a function, so return doesn't make much sense. Yes, very good. So indeed, so basically you have letters, which is a list, right? You're appending, so letters is essentially going to be a list. So to visualize your data there, you just do print. That's totally the correct option. All right. So yeah, you can also do conditionals. So sometimes you may say, okay, I want to skip the odd indices, or I want to skip the even indices. Then the complication that you can add to your list computation is to add an if clause. Okay, so that's also doable. So this is list satisfying some Boolean conditional. So here, using list comprehension, what are we doing here? This is x squared for x in range from 2 to 16 if x over 3, well, the remainder equals to 0. So this is saying this is for make sure to analyze on pen and paper or basically in your mind to see what happens. So that for part, okay, that's really natural. This is just the mathematical thing. It's written in syntax. So x in range from 2 to 16, that's what? That's 2 all the way down to 15. That's the indices. And then what are we doing here? We're doing the square. Okay, so this is just x squared. There's nothing special there. But then here it says what? It's if x divides 3. That's saying what? That's saying actually I'm picking 3, 6 all the way to 15. So that's the if clause that's giving you some restrictions on x, right? And of course you can change it to remainder being 1, remainder being 2. So that's basically really up to what kind of thing that you want to do. So that's doing what? That's doing 3 squared, 6 squared, all the way up to 15 squared. So if you want to write a loop, then the one at the bottom is now if you look at it, this is the same thing. That is for I in the range, the same thing here. And then you have an if clause that's added to your uh to your loop. And then you are just appending the element squared. So essentially they're equivalent, but you can do the list comprehension to make your code more efficient. Right? So this is kind of like what? Like one line comparing to 4 lines. So this is you build up a you set a default list L, and then for the loop for the conditional that are going to be 2 lines. Finally, you do need to append your list. Okay, so that's a total of 4, which is uh sort of can be avoided. Okay, so can be condensed. Right. All right. So yeah, well, let's play with this one. Okay, so this is a finger exercise that's somehow I just gave you guys a hint a little bit earlier. Use the list comprehension to make a list that has the entries as all possible sums of the elements in the 2 lists. Okay, so I have 3, 5, and 6 in the first list, and 10, 13, and 27 in the second list. But I'm adding one number from the first list with one element from the second list. So it's going to be a total of 9 possibilities. So how are you gonna do that? So this is if you have downloaded your notebook, you can add a code cell right here to play with it. Okay. So let me see if I have that copy in my page. Yeah, it's here. So for the live coding lecture 7, it's also here. So you have the 2 lists. You want to use a list comprehension. So that you can also fill at this place. Think about it for 1 minute. And of course, if you know an answer, just let us know. So which one do you think is the correct answer? So why? What's the reason? Okay, okay. Yeah. So yeah, they also try the other two. So basically you're saying, okay, I'm adding X from A and Y from B. So here, yeah. If you are really familiar with the indexing, it's also reasonable to do indexing, let's say for AI. Uh, so for I in length of a range of length of A, and then you do AI, right? So that's also a way. So let me write that also. So this is uh some 0 equals to, that's also totally acceptable. So for I in uh uh range of length of A, so essentially it's going to give you the same thing. And this is J. And I do AIBJ. So yeah, well, if it works, that's great. But think about the other um, synthesis and why. What's the difference? So so let me also share the screen there since it's not shared from that end. So there is a difference. Okay. So this is saying what? This is saying basically I'm constructing a list. But now, basically, this is saying my running index is according to X in A. So that's this kind of thing. Okay. So this is basically I'm saying I pick a Y in B, so which is like 10. But now I'm constructing like a sublist from you running through A. Okay. So that's the 13, 15, and 16. And then uh, it's gonna get into 13 as my B value, and I'm getting 16, 18, and 19. So that's the second sublist. Okay. So essentially, if you use a pair of brackets, essentially that's data structure that you do. Okay, so you can say this is a one liner for sum two, but this is actually two list comprehensions within one line. So I have one list that's enclosed by this kind of comprehension. Okay, expression, element in the set, is in the list, but then I'm putting it within another comprehension there. So if you think about this structure, this is eventually going to be a matrix in NumPy. Okay, so just as a heads up. And if you do it in another way, so if I run through B, and I then for every X, right? For X value from A, I decide this sublist. That's going to be what? It's going to be 3 adding to 10, 3 adding to 13, 3 adding to 20, 27. That's this one. Okay, so it's really up to the order that you add. All right, so yeah, well, that's of course, if you are running I and J as indices, you can do also reasonably using this one-liner. Mm, yeah, I'm thinking about a way to. So what's the distinction here? Yeah, the distinction here is clear in the sense that for the sum right here with no indices, you cannot really give reasonable conditionals for indices. Okay. But here, if you have restriction on your I and J, then you can put them afterwards. So as the Boolean expressions. So let's say if you only say want to add odd I and even j to specify certain choices, then you can do this. But then if you are just saying, okay, I grab everything from A, everything from B, and then combine, then that's just without indices. Right. So was it good? Yes.
So for some zero, it would be easier to modify and like add conditions.
Exactly. Yeah. So you have I and j that you can do for conditionals. Here so this is sort of like the input and output, right? So for the conditionals here, you need to do the conditionals for x and y. So then you would say, okay, what I'm gonna be selective on the outputs and combining. And this here are gonna be sort of like the conditionals on the inputs on the I and j's and combining. Yeah. So yeah, so it's gonna be I and j. Here, yeah, let me try something like this. So it's a sort of experiment that we can do. So I can do if AI divides 2. So it should be fine. So yeah, well, if you want to manipulate the output, I think it's still fine. So just make sure I have okay, I have an even number. So let's try that and see if it works. Yeah, oh yeah, okay. So just now in a second there's the not closing bracket, so I was kind of confused. But now you see what's going on here. So it only allows AI to be odd right even, right? So AI is this one. So you're only adding 6 to the list B. So yeah, indeed, for sum 0, you have a freedom. So you can manipulate the output, you can manipulate the input I. But here now you only have these things that are available that's for your conditional. Okay, so you can say what happens with X, what happens with Y, or I can say for yeah, let's see this. Okay, so if X plus Y uh, is 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 odd. So I'm only getting the odd numbers and see what happens. Oh, 2. Oh, that's still fine. Just to make sure. Yeah, 1, 2, 3, 4. Yes, these are the numbers. Now I'm only allowing the output. Okay, I'm only allowing this expression to be odd, which is totally fine. Okay. So it's really up to what kind of so the point here is it's a little bit harder for this kind of expression syntax to restrict the inputs, especially the location I and j. You can do so yeah, well, yeah. But then here you do have a little bit more freedom. So you can manipulate A, you can manipulate B, you can manipulate I, you can manipulate J, and all kinds of combinations. So that's the distinction there. So I can change I to just divisible by 2. And then that will give me a restricted thing. Okay, so it's going to be A equal to 3 and A equal to 6. That's going to be a total of 6 elements right here. Yeah. Yeah, these are the things you definitely can play with. Question? Yeah, make sure to play with these to see what kind of things that you can do, and if there's any error, then what's gonna be the cost? Yes.
Why would this go by 2? But 3 is not divisible by 2, so why would it be complete?
Which one?
Sum 0.
Sum 0. Okay.
It's 2.
I divides 2. Yes. Oh, I is the index in the range of length. Yeah, so
0.
yeah, that's here. That's my index 0 and index 2. So which is exactly the difference between the first the sum and the sum 0. So in the sum, you want to specify the location. That's going to be a problem. That's the distinction. Yes, make sure to note that. Uh, I'm saying I'm allowing the zeros and the second indices, which is not easy to do in the original sum. Okay. But of course, for the outputs, right, for other things with x and y, you can do whatever you want. All right. So now let's move on. So yeah, okay, that's the finger exercise we have done. So yeah, well, we still have some time. So lambda functions. So this is this is actually a nice figure in one of the textbooks. The lambda here. Okay, so that's the lambda function. Essentially, what does it mean? It just means it's an anonymous function. So you define a function, but you don't specify a name, which is something really interesting. Remember from earlier, so let me highlight. So without a name, so you do not really need a name for the function, especially if it's not really uh, explicitly called many times. So let's say if you define a function that's called my function, essentially you are sort of like have an implication that it will be called in somewhere, right? But suppose that function is not really going to be called multiple times, then you don't really need it. So here we have to give a function name for the original definition of functions. And here the lambda word is reserved. That's trying to indicate that, okay, I'm going to define some function, but there's no name to the function. And the way you define is basically arguments, colon, and then the expression of your arguments, okay? Just computing the output, okay? So this is the input, output. So this is the way that you'll be able to define a function also in one line, okay? Define a function in one line without naming it, okay? There's no name. And here, what we know is that the arguments, you can do many arguments before the colon, but you can only have one expression after the colon. So this the only one. Okay, so one expression. That's right here. So a really simple example is this one. Okay, so let me zoom up a little to the maximum. That's the best we can do. So what does it say? Basically, here, so in the line, we focus on the left on the right hand side. Okay, this side. The left hand side is the function name. So h equals to lambda xyz colon x times y times z is essentially saying for the right hand side is mapping xyz, the arguments, to the scalar output of x times y times z. So that right hand side is exactly a function. Okay, it just says how your inputs are associated to the output, but then that thing on the right hand side is a function already. So when you say h equals to that, it just says, okay, my h letter now represents this function. So if you want to say there's a name, then h is the name, but it's not needed. Here we want to call it, so it's h of 2, 3, 5, and you are giving a name to it. Okay, so this is a name, but not needed. And that's our lambda function. Okay. So That's already a function. So does it make sense? So yeah, well, basically we're talking about this because one thing is that sometimes you want to have a simple expression for to return as a function. So earlier when we define a function, it's we have a function, whatever. You have a number as input, you have a number as output, but sometimes you want to return the function as an output, which is like, let's say you have a function f of x equal to sine of x. You want to output the derivative, which is the cosine of x. But cosine of x is actually the function you want to return. So which is why you have this kind of lambda expression at the return line of your operation. So this is a discussion right here. We are not really experts on lambda calculus, but this is a fundamental thing in computer science. So this is a lambda calculus that's making in the computers variable binding, substitution, function abstraction explicit. Okay, so if you are interested, make sure to take a look at these resources. But basically, these are the fundamental backgrounds, okay, of lambda calculus back in 1930s, where computer science evolved really evolutionary. But at this point, okay, what's here? So one example that we are discussing is that let's say, okay, you have a function, right? So the differentiation of a function is actually something associating an input with an output, but both are functions. Just remember. So the dx of any function, this is the derivative. But what does it do? So it gives me a function f, it returns f prime. So this is a function, this is a function. So essentially, you want to do it in a nice way in computers. So you want to return a function so that you can plug in a and you will still get an answer. So that's the purpose. And as a reflection on this example right here, so this part, okay, this part is what's needed only for the input of my derivative. Okay, that's not the important part. The important part is here. We're using a slope of the secant, okay, to represent the derivative, just an approximation. So, but here this is the simple implementation, which is the slope of secant. So if you want to sketch a graph, let me do it quickly. It's basically you have a graph and you change the input by 0.001. And then you use the slope of the secant to approximate the slope of the tangent. Okay, so that's what you're doing here. But notice the line, lambda x colon f of x plus dx minus f of x, whole thing over d of x. So you need to provide my f as a function in order to calculate the difference here. There's nothing mathematically complicated. You just have, okay, f evaluated at a point minus f evaluated at another point over the input difference. So the right hand side, the expression is super simple as long as your f is provided. But now notice f is provided as a function, which is here. Okay, that's my input of a function. So let me be really careful. Function, that's f. But then you want to return a function, right? So that's where your lambda function comes into play. So you don't really care about the name of the function. You just say, for whatever x value I give, you give me, I give you this fraction. That's an output. That's the approximated derivative function. Okay. So yeah, right. So make sure to play with this cell because it represents the output of my derivative of f as a function. Okay, so that's the key here. And of course, now you use that function, right? So then you can use the bracket 0.5 to evaluate the derivative at the point. Okay, so this is essentially f prime of 0.5. This is indeed my f prime. So the type of this is a function. Right? All right. So okay. So Wednesday is the exam. So we're gonna continue next month, the Monday after the break. But of course, if you have any questions, just let me know.